Yeah, hello, welcome back. This is um, uh, the revision on frequentist statistics and Bayesian statistics. So, as we discussed last time, these are the two main approaches to statistical inference. Um, they're more or less developed really in the 20th century because when Fisher and Pearson made the point that what they're doing is classical statistics or frequentist statistics. Uh, Then the other camp became the Bayesian statistics. I think before that, people didn't really worry too much about these issues. They probably didn't have data, they probably didn't have computers, they didn't have ways of calculating things. So that's why it really became important in the 20th century only. And frequentist statistics is the majority of statistical approaches, and people working in these areas typically use this approach. At least, let's say 80% and maybe 20% prefer the Bayesian approach. So one important concept is the maximum likelihood principle. The likelihood is simply the probability of the data given for a certain parameter value. And the maximum likelihood principle simply says pick the parameter vector W, which explains your observed data the best. And you can use a few tricks here. The first one is to assume that your data was generated independently. Then you can turn this multivariate distribution of n vectors into the product of the probability distributions of each individual observation. Um, so here you have this product from I equals 1 to n. And this is a probability uh, of explaining this data point xi given the parameter values. Um, Often it's more convenient to work with the log of this expression because the log of the product becomes the sum over here. And then you get the sum over the log of the probability distribution of the x. And the maximum likelihood estimator is a maximizer of either this or that expression. So the maximizers are the same for in both cases. Our favorite example is the linear model, which is already quite powerful because you can think of working in a basis function space. So here it is written in vector form. So this is a scalar product plus some noise. And we make an assumption, for example, that this noise is Gaussian distributed with mean 0 and some width sigma square. So this is this assumption which can be discussed. Sometimes this is not a good assumption if the residuals are not Gaussian distributed. So in the best case, that's something one should check, but it's also a very convenient assumption, as we can see in a second. And that's all because we can now write the probability of yi given x, where we just substitute epsilon I with yi minus xi transpose w. We see that over here. And this is now the probability of the y given x. Has this also very convenient Gaussian formulation. And when we talk, we can take then the log of this expression, and we get the log of this vector in front. So this squared can be written as bracket the power of minus 1/2. So we end up with a minus 1/2 in front, and then the log of the argument, which is the log of 2 pi sigma square. And the log and the exponent cancel, so we end up with minus 1 over 2 sigma square, and then the difference between the prediction and the actual measurement squared. Then if we consider all the data points, we have to multiply this factor in front by n, because we have n data points, and then here on the right side we get the sum over these differences here, squared. And if we take the maximum of this expression, first term doesn't count. So if you assume that sigma square is fixed or of no interest, and then what we are essentially doing is minimizing the error here because this is a minus sign over here. So the solution is that the maximum likelihood estimate is the same as the least squares estimate. So this gives us a nice reason why maybe the squared error is a good thing, because squared error is related to the Gaussian assumption in the likelihood model, and so maybe it gives you a better intuition why choosing a squared error, least squares approach might be a good idea. And this is the frequentist experiment. Essentially, we have an unknown parameter, so it's unknown but fixed. Based on this parameter, data is generated. Then we have an estimator which tries to estimate this parameter, and then maybe get this value out over here. And this is what we are doing. But we imagine that we could repeat this process many times, L times, goes to infinite. And so we think, okay, we generate data again, we make the estimate, and then we do that. And in principle, we would see a distribution here of estimates, because every time we see a slightly different data set, and we would get a different estimate. And then in the frequentist approach, you would try to analyze how this distribution scatters around the true value. And then you evaluate, you make a hypothesis about the center, and then you analyze if your observed estimate sort of violates that this hypothesis is true. So what you are typically calculating is the probability distribution of your estimates given the true parameter, which is typically centered. You have an unbiased estimator around the true parameter, and then with a variance which decreases with the number of data points. So this assumption permits you to do an analysis. The Bayesians sort of criticize that you have to make this imaginary assumption about these imaginary additional data sets, which you don't really have, which they think maybe is a little bit unnatural. So the competing approach is the Bayesian approach, which has a lot of similarity with the likelihood approach, but also some important differences. So here we see the likelihood function, the probability of the data given the parameters. But then here we see a second term, which is the probability distribution over the parameters. And it's not conditional data. So this is something you have to know before you do the experiment. So the user has to make some assumption here about this so-called prior distribution. And this is what the frequentists or the classical statisticians would criticize, because it seems to introduce some influence of subjectivity, which is maybe not scientific. The advantage is now, I mean, in a way, it's simpler because you have a complete model. You have a probability distribution about W, and the data given W. And as we know from before, this is a complete probabilistic model about W and the data. And then what we, for example, can do, we can apply a Bayes formula and calculate the posterior probability, which is the probability distribution of the W given the data. And this is something the frequentists cannot calculate. They do an estimate and then analyze the properties of the estimate. But a Bayesian approach, and this is a great advantage, gives you the full posterior distribution of the W's, and gives you, in a way, much more information from the data. So this is a Bayesian experiment. We assume that mu, so the parameter, is drawn from a distribution, and this distribution is a famous prior distribution, which we have to put in. And there's some argument that anybody has to put in some assumptions. The frequentists would debate this. And this debate between Bayesian and frequentists has been going on forever. From a machine learning point of view, we think both are fine. and we take the one which seems to make more sense in a particular application. So we have a probability distribution over the parameters. Then we have data. So we have, and we can calculate the probability for the data given the mu. And then in the Bayesian approach, we can also invert this and calculate the probability distribution of the mu given the data. And if you look at P mu before and P mu later, after the data, then it's narrower, it's more peaked, and it's centered not around zero, but maybe close to the true value of mu. If you get more data, this will get narrow, and hopefully the maximum will become closer to the true parameter. And we see this also in this posterior distribution. So if we go to many data points, then we have here the mean, so the mean estimate of the data, and here we have sigma squared divided by n, as in the frequentist approach. And if we have a small number of data, then it will be drawn more to the prior distribution, which was assuming a zero mean and a certain variance here. So that's why this is smaller than the true. So it's called a bias, which we introduced. Yeah, we can look at our favorite linear regression model. So we make an assumption about the prior, which is can be the simple Gaussian again centered at zero. And here we are penalizing the sum over the wi squared. And here we have something like an assumed variance for this distribution. This is what how we would formulate convenient prior, let's say. Then we have the likelihood, which we know from before. And when we calculate the posterior, we have to multiply the prior with the likelihood and then normalize. And after some manipulations, which are not terribly complicated but time consuming, we see that the posterior distribution has this term, which is the sum over the wi squared divided by 1 2 alpha squared minus this term. And when we take the log of this, okay, first of all, we see where is this maximum? This maximum exactly, because here we see a weight penalty. Here we see the least squares error. So it turns out the map estimate is exactly the least squares estimate, the penalized least squares estimate, sorry, penalized least squares estimate we've seen from before. Now we had x transposed x, so this is the design matrix. And here we had the lambda before, and now we have sigma squared divided by alpha squared. Again, we see that there's a nice explanation now why penalized least squares is a good idea. It corresponds to the map estimate under the assumption of a Gaussian prior for the parameters and of a linear function and Gaussian noise. So in a way, if we can have good estimates for sigma square and alpha square, we don't have to search for lambda anymore. We can just plug it into this formula, which I think is quite neat. Yeah, when we do the Bayesian prediction, life can become quite complicated. First of all, even when we can if we can calculate PW given D, the form might be not very easy to interpret. So that's one problem, because this W lives in some high-dimensional space. And how do we know how this looks like, even if we have the mathematical formula? And the other thing is, if we make a prediction, so this is a prediction of y given a new x and given our past data, then we end up with this integral we have to solve. And this is not easy if p of w given data is not an easy expression. So this has to be approximated by some integration method like Monte Carlo integration, and this can be quite involved. So you might have a preference for the Bayesian approach because it gives you more information, and in a way it's a nice principled way. It's a pure application of probability theory, but then in practice it can become quite involved, and people are working on researching on good ways of approximating this integral over here, for example. Um, so this is one reason why the frequentist approach is more popular. But in machine learning, as I said, we don't care too much about philosophy. We want to have something that works. And as you all know, we're using penalty terms in deep learning. You can interpret them as being implicitly a Bayesian prior. You can also say, oh no, it's just penalty term, has nothing to do with the Bayesian analysis. So in many ways, the um, deep learning is more a frequentist approach. You don't do Bayesian integration. On the other hand, there's ongoing work which tries to integrate Bayesian thinking also in deep learning. In particular, it might give you a better estimate of the uncertainty in your prediction. Where deep learning is typically overconfident and doesn't give you a lot of insight about the certainty of your prediction. And even if the network is quite wrong, it might be very certain about a wrong prediction. So I want to switch to the other. Still running, I hope. Yeah. Okay, so let's look at the other thing we covered last time. Is a support vector machine. So it starts from a different intuition, but then you get also at the end you end up with a cost function term, which then sort of fits nicely into our framework we have been discussing before. So we have data points with targets 1 and 0, so green and red. And in this case, so x1 and x2 are the two input dimensions. And in this space, the two classes can easily be separated. But then they can be separated by many hyperplanes. Which one should we pick? And the principle of optimal separating hyperplane introduced by Webnick and Chervalenkis says we should pick the separating hyperplane which has the largest distance to the data points in the respective classes. So this C, this term C here, which is this distance, which is also called the margin, so it should be as large as possible. And the data points which define this separating hyperplane, they're called the support vectors. That's why this approach is called support vector approach. So in this case, the closest one would be these three data points. They are the support vectors because they define this line, because this line is maximum distance to these data points. And in a way, we can remove the rest because they don't play any role anymore, or we can have a slight disturbance here. So the support vectors are really the important quantities of interest. And we can formulate this as an optimization problem. So we want that Wi times Hi is larger or equal to 1, not just larger or equal to 0, but larger or equal to 1. And under this constraint, we want to use the parameters, the W's, which have minimum length, so the square of the components overall components should be minimum, whereas we leave out the W naught. So it's not making any assumption about W naught, only because it goes from W1 to WM, and W naught was the offset one. So the model has the W naught, it's just not penalized in this situation. And by doing that, we can see we get what we want. And so this is a different plot. We have X for input and Y as output. And these are the targets of some training data points. And we want the function to be at least 1 and minus 1 when they hit these data points. So this blue line could be sharper, it would be have a higher slope. But if we minimize the slope here, so we take the one with the smallest slope, we automatically hit these support vectors here. and the distance of the point where the transition is from negative to positive as the largest distance to the data points. So this is the way we can formulate this intuition into a cost function we can then solve. And the cost function is quite difficult to solve. We discussed it a little bit, and if you want to really understand it, you probably have to consult the corresponding literature. The support vector machine can also deal with data which are within this boundary of 1 and -1, and maybe even on the wrong side of everything by introducing these sort of slack variables. So this is shown over here. So we don't just want this expression to be larger or equal to 1. It can be larger or equal to 1 minus this psi I. But psi I should not be too large. It's constrained. It's be larger than 0, and the sum should be smaller than some other variable, 1 over gamma. And if we formulate this, then we can also write this whole thing in this form. So here we have a typical weight decay term or weight penalty term, and this is the cost function. It's the positive of the magnitude 1 minus y times h. And this gamma sort of determines how much we are enforcing this constraint. So if we select gamma to be really large, then we say, oh, definitely this constraint needs to be fulfilled. If we make it smaller, we allow more slack, because remember gamma was here. If gamma is large, then the sum must be small. Yeah, then we compare the different cost function terms for the different approaches, and we see the support vector machine one is here, goes with the slack variables, and increases linearly, and this increases more steep when gamma becomes larger, and then here it doesn't have the cost function at all. So the support vector machine was quite popular. So from the mid-90s to the 2010, 2011. It's very practical, easy to use. They have nicely packaged and very robust software which is available. So if you don't want to spend the effort of training a deep neural network for your application, the support vector machine is still a very good option, as are other kernel approaches. They all have some problems with scalability. With n the number of data points is more than, let's say, 50,000, 100,000, then this can become quite slow, and also we get a lot of support vectors which also make the prediction slow. But if that is not a problem, if you're far away from these 50,000, 100,000 data points, support vector machine can be quite powerful and is quite popular. Still, it has been quite popular. Of course, now the research has moved into deep learning, but who knows? I mean, I think people still appreciate support vector machines. They just don't do so much research anymore in this direction. But in applications, it's still used a lot, and it's a very good approach. And as I said, you get packaged solutions which are easy to use, only a few parameters to tune. So of course, if you use the kernel formulation, you have to select the kernel, and maybe you have to tune one parameter in your kernel, and maybe estimate the noise variance. So there are maybe 1 or 2 parameters, but not a huge number like in deep learning. And it's the problem is convex, so you get a unique solution. You don't have several optima you have to worry about. So a lot of has a lot of theoretical nice properties, which made it so popular during the time when neural networks were not very popular. Okay, thank you.